Hello, welcome to the seventh talk of the Chromatic seminar. So today's speaker is Logan Hyslop from UCLA, and Logan will be talking about Morava Stabiliser groups and Bousfield Localization. So Logan, please take it away.
All right, so today we're going to start with our Morava Stabiliser groups. So we have a nice little joke here to start us off. Why do cows love chromatic homotopy theory? Because they really like to move. All right, so our story today starts with, well, we're going to fix first a prime p and some level n, some finite level, and we're going to try and study the nth part of the Morava Stabiliser group. Of the moduli space of formal group laws. So the nth place in filtration, which classifies our height n formal group laws over the prime p. So recall that over an algebraic closure of FP, we're going to fix this one once and for all. Then we have a unique up to isomorphism formal group law f of height n over this field. And what this gives us is going to be a map from its spectrum to this moduli stack of height n formal group laws, classifying this formal group law itself. And whenever we have another ring R, we recall that we can form a pullback given some map from R to this moduli stack. And this top map is going to be a inverse limit in schemes of étal extension. So this is a pro-étal map in modern language. So in particular, we can do this with R equals FP bar. And what we're going to get is this, what we're going to call spec B. Mapping to spec FP bar. Yes?
I'm sorry, yeah, can you please recall, just recall what a pro-étal map is.
Okay, yeah, sure. So a pro-étal map here means that spec R prime is equal to the inverse limit of spec Ri, where spec Ri to spec R are étal, or equivalently that R prime is a direct limit of Ri, where R including into Ri is étal. In Lurie's notes, he doesn't call this a pro-étal map. It's a little bit more modern language, I guess, but he calls it just a direct limit of étal maps. But really what it means is a pro-étal map. This is very useful in arithmetic geometry, especially in tilting scenarios, which is going to come up with the chromatic Nullstellensatz, the tilting at least. All right. So we can do this in particular with R equals FP bar. And we're going to get a diagram of this form. Now, FP bar is algebraically closed. So any étal extension is a finite coproduct of copies of spec FP bar. So just some finite set. And in particular, spec B is an inverse limit of finite sets. So we can identify spec B with some profinite set. which we call boldface G. And this is just a recollection of the fact that if we look at the pro-italicite of a point, so by a point I mean something which is a point, so the only italic extensions are co-products of the scheme itself, so spec of an algebraically closed field, for instance. This pro-italicite is just profinite sets. All right. So this is the start of our story today. So we can look at points in G, which are going to be, so some geometric point, we're going to take some K algebraically closed over FP. We're going to have maps into spec FP bars, so one over here and one over here. So we might as well call this eta and eta prime. I'm going to use Lurie's notation here from FP bar into K. And such that when we map these in by F here and F here, we're going to have two formal group laws, which we can call eta of F and eta prime of F. And these are going to agree as formal group laws over K. Now, since K is algebraically closed, there's only one formal group law, and we may as well assume that spec K is equal to, that K is equal to FP bar by replacing it with something smaller if necessary. And then we can choose one of these. So say we can choose eta prime is the identity on FP bar, because we can just change it by an isomorphism. And then what we're going to have is we're going to have the formal group law F and some eta maps FP bar to itself, so something in the Galois group, such that eta of F isomorphic to F here. Okay, so what we're going to get out of this is we're going to call out F P bar comma F these pairs of automorphisms of FP bar together with some isomorphism like here, which are going to be which is going to be G. And this we can see fits into an exact sequence. We have 0 to out F. So these are the automorphisms of the formal group law, which keep the field fixed. This is going to include as a normal subgroup of this bigger group, which is going to have a surjection to the Galois group of FP bar over FP to 0. And we know that this is just the profinite completion of Z. So this map here just projects off to the automorphism FP bar. Okay. And we want to try and study what this group here looks like. So to this end, we're going to look at properties of our formal group law F. This guy is what we call, let me just write a definition before we go any further. Out FP bar comma F is equal to G will be called the Morava Stabiliser group. This is what we intend to study today. And because we have this sort of italic extension, we can note that we take spec FP bar, which is acted on by this group G, just by this pullback here. And we quotient by it by the action of this group. then we're going to get back this moduli space of height n formal group laws. This just sort of repeats the fact that, or rather, this is a sort of a reflection here that this is what you could call a pro-étale algebraic space, because it's a quotient of a scheme by some pro-étale equivalence relation. Okay. So what can we do to try and figure out what this guy here is? Because this really is what because we understand what spec FP bar is. So if we understand this group, then we can have some hope of classifying this MNFG of what this guy looks like. So we need to continue to look at what this here actually is. So we start by looking at our power series F. So this is going to be some formal group law over, let me just write formal group law of height n over FP bar. This uniquely determines up to isomorphism. And our first step is to look at what this group here is. So we have that out of F is equal to the group of units in this ring, end of Fx. Recall that end of F is the set of power series G in FP bar of X, such that G of F of XY is equal to F of G of X, G of Y. And this is a ring where multiplication is by composition. And G plus H is equal to F of G of X, H of X as a power series. So this formal group law is just telling us how we do the addition on these endomorphisms. Excuse me for a second, I have to blow my nose. Okay, so we reduced to wanting to understand this ring here at end of F. And so recall that we have our Frobenius. So we're going to call this pi as an element of end of F. So pi is going to act by pi of F of xy is equal to, let's see. Do you want to do that yet? Okay, maybe I don't want to define that yet. But to this F, this formal group law, we can form another formal group law F to the P, where this is just going to be, we're going to take F of xy is equal to some aij x to the I, y to the I. And then we're going to map this to F to the P of xy is just applying the Frobenius endomorphism on all of these coefficients. Should be y to the j. This is going to give us a new formal group law because we're in characteristic P, so this Frobenius plays well with respect to all of our structure. And we just need to, and we're going to use this to sort of find some more elements in this endomorphism ring of F. All right. So this is another formal group law. It's also of height n, so there's an isomorphism from F to the P. And we're going to take some isomorphism here, and we're going to call this nu. So nu of F to the P of x comma y is going to be F of nu of x, nu of y. And note that if we were to take our formal group law and just raise it to the power p naively, this would be the same as taking this f to the power p, and then we can do the Frobenius on each of the elements. So what this means is that we have, using this isomorphism nu, if we do nu of f of x comma y to the power of p, then this is going to be the same thing as, well, we can pull to the power of p out because nu is some endomorphism which behaves well with respect to these powers. So this is going to be nu of x, f of x, y, power of p. Sorry. This is nu of f to the power of p of x, y, to p, y to the p. This is what I want to do? I think so. We can do nu inverse. Nu f x, y, nu inverse of x, y to the p. So this is nu inverse of f to the p of x to the p, y to the p, which is equal to f of x to the p, y to the p. So in particular, if we do is this what I want to do?
This looks weird.
This should be news in here. Yeah.
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 Oh, no.
Yeah, it should be nu, not nu inverse.
Yeah, it should be inverse. Yeah.
Yeah, right. Okay, sorry. So this is f to the p of this should be
so
f,
the last one
f to
should
the p.
be f. It should just
Yeah.
be f. Yeah.
Yeah, f of nu of x to the p, nu of y to the p. Right. So in particular, if we take pi is equal to nu composed with the Frobenius map, this is an endomorphism of f by the above. Okay. And this pi is going to form some sort of a uniformizer in this endomorphism ring. So in particular, if we're going to take G in and F arbitrary, then G is a power series. So it has the form of B0 T plus B1 T squared plus da, da, da. And so either B0 is a unit, and then G is a unit, or B0 is equal to 0. And if B0 is equal to 0, then G of T is G0 T to the P for some power series G0, as we've seen before. So what we can do here is we can take G0 of nu inverse, and we can compose this with nu of the power of P map. And then this is going to be G0 of the power of P map, which is equal to G. So that G is equal to, we call this G prime pi for some G prime in the endomorphisms of F. So any non-unit can be written in the form of G prime times pi for some G prime. So every non-invertible element has this form for some of these, and I mean conversely, anything of this form is not invertible because pi of t is equal to something. Well, the zero coefficient of pi is zero, so it can't be. You can't get to something invertible there. What's also important is that end of f is a sort of domain, so any two non-zero elements compose something non-zero, which is easy enough to see just by looking at the power series. The smallest coefficient, smallest non-zero coefficient in both of them is going to be still non-zero in the composite. So every non-zero element we can write, in fact, uniquely as G is equal to G prime pi for G prime uniquely determined in this endomorphism ring. And then we see that as a corollary, end of F is a local ring over over FP bar. I guess, yeah, let's just say it's a local ring for now. I'm going to suppress this for the moment, at least, because it's not necessarily characteristic P. Yeah, it's actually not characteristic P because the P power series is not 0 on this because it has height n, so it's not over FP bar. Sorry, but it is a local ring. And in fact, it's an analog of a DVR. It's non-commutative, but it basically would be a DVR because we can define, this is different new from before, but we're going to map this to Z, union infinity, some sort of discrete valuation. Nu of G is equal to n, where G is equal to G prime times pi to the n, where G prime is a unit and is uniquely determined with this property, and is actually greater than or equal to 0. And by convention, we take nu of 0 is equal to infinity. So with this in mind, we can easily see that we have nu of GH is equal to nu of G plus nu of H, and that nu of G plus H is less than or equal to, wait, sorry, I think I want greater than or equal to the minimum of nu of G and nu of H. Right. Yeah, that is what I want here. Okay. So nu is an analog of a discrete valuation in this non-commutative setup. Okay. And now as a fact, we have that this endomorphism ring of F is complete with respect to the valuation nu. To see this, you can kind of just look at what things might have to be modulo this uniformizer pi, and you can inductively build up formal endomorphisms of this formal group law in order to show that if you have something which converges in this valuation, then it converges to some endomorphism, just by general continuity properties. All right, and with this in mind, this is, like we said, a domain, so we can form its total ring of fractions. So this is just inverting all non-zero elements, and we're going to call this D. And in fact, D is some division ring. Note here that we're going to have the valuation of P. So if we recall that we defined, well, 1 was defined just to be X, and then F of X comma, or let's say F of N of X. So this is just the N comma X. So this is taking N plus 1, since F determines our addition, is equal to N plus 1. So just by definition of height, that so P in this ring, if we apply this, then this is going to be lambda T to the P to the N plus whatever else. And in particular, we're going to have that, so this is where N is the height of F. So the same N from before. And in particular, we have that the valuation of P is equal to N, because this is the coefficient of the smallest power of P. such that the coefficient of t to the p to that power is non-zero is going to be the same as the valuation of your given power series by what we defined earlier. All right. So in particular, what this means is that p is topologically nilpotent. So the canonical embedding Q into D extends uniquely to QP into D. So QP is the completion of Q at the prime P. And D is here some, like we said, some division ring, and the valuation nu extends the valuation on D and still determines a well-defined valuation, making D a discretely valued division ring, not quite a discretely valued field, but almost. Okay. And now we note that for any y in D and x such that x has valuation 0, the valuation of y x y inverse is equal to 0. So we have that conjugation preserves this degree 0 part. And so descends to an automorphism of, so we're going to take the endomorphisms of F. So this is everything in D with valuation greater than or equal to 0. And we're going to quotient out by pi times the endomorphisms of F. And this is going to embed into the algebraic closure of FP bar. So this is just some actual, well, it's a finite division ring, so it's a finite field, and it has characteristic P since pi divides P, so it embeds into FP bar. And we're going to see that if we act on this by Y, so we want to see that the conjugation action is determined by Y. We claim the conjugation determined by Y is the nth Frobenius, or the nth power of Frobenius, where the valuation of Y is equal to n. Okay. So to see this, what we can do is we're going to take any G in the endomorphisms of F with G of T is lambda to the P to the nu of G. This is again by definition of nu. And then we're going to have plus higher order terms. And that's not equal to 0. And then we're going to take B and FP bar and H a power series with H of T is B0T plus dot dot dot, bunch of higher order terms. H prime is going to be G of H of H, of G inverse. And then we're going to have that G of H is equal to H prime of G, just by definition of this, because we have this G inverse here. And so we can see what happens if we act by G of H of T, then we're going to get lambda times B to the P nu of G. So B0 to the P nu of G. And then T to the P to the nu of G plus higher order terms. And on the other hand, this is equal to H prime of G, where H prime is equal to the conjugation of G applied to B0, T to the P, sorry, just T plus higher order terms. And now H prime of G is equal to lambda times the conjugation by G of B0 times T plus dot, dot, dot. So the conjugation by B0 here, conjugation by G of B0 is equal to B0 to the P to the mu of G. So this shows that conjugation by G of B0 is nothing but B0 to the P to the mu of G, which is equal to the nu of G's power of Frobenius, as claimed. Okay. We can, yeah. So this is explicitly using the endomorphism from end of F, sorry, the morphism from end of F over this into FP bar, which we can describe explicitly by taking any power series B0T plus dot, dot, dot. This is just going to go to B0. And this kills pi end of F, so it factors over this quotient here. And this being subfield shows that this is an embedding. And in fact, we have another claim that the image is nothing but f p to the n. So it is a finite field of order p to the n. So to see this, we can note that this is going to be surjective, since whenever we have any endomorphism, let's first show that this actually lands in here. So for any endomorphism, G is B0 T plus dot dot dot. G being some endomorphism of F in particular means that G commutes with P here, which is in the center. So we have this equality. And we have that P of T is equal to mu T to the P to the N for some mu plus whatever else. This is again just because this, F has height N. So if we do G after P of T, then we're going to get B0 times mu times T to the P to the N plus whatever else. And this is equal to, if we do P of T after G, then we're going to get mu times B0 to the power of P to the N plus dot, dot, dot. This should be T to the P to the N. So in particular, if we compare coefficients, this versus this, we see that B0 is equal to B0 to the P to the N. So B0 lives in FP to the N. And to see that this is surjective, note that if we ever have B0 satisfying this claim down below, we can lift it to a solution of this and then inductively build up so that we have power series, which gives an endomorphism of F with leading coefficient B0. A little bit sketchy, but that's roughly the proof. So in particular, this shows that if we're looking at the Frobenius determined by the action of this endomorphism on the degree evaluation 0 part, then we get a surjective homomorphism from not even NF without 0, but DF without 0. It's surjective from either D without 0 or NF without 0. It doesn't really matter. To the Galois group of FP to the N FP to the N over FP. This is surjective. In particular, we can show a few more properties about D. So we can actually show that D has dimension n over FP, over QP. To see this is actually dimension n squared. This is because if we look at the degree 0 part, then the degree 0 parts modulo degree 1 part has degree n over the residue field FP. So we can take n different lifts, and then because pi multiplication by pi is going to determine isomorphism on levels, we can take a basis of lifts of a basis of FP to the n over FP, and then we can just take, so if we have like A0 pi to the I dot 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 A n pi to the I, let's start with A1 then. For 0 is less than or the I is less than n, this is going to give us a basis because P has valuation n. So we can always assume that an element has valuation between 0 and n minus 1. And this has cardinality n squared. So we get the claim. So another corollary of this that we can note is that, actually, let me do a claim. Because proposition. D is a central simple algebra over QP. So we know it's an algebra over QP. We know QP is contained in the center. We want to show that it's central simple. So we're going to take any G as an element of D with G not in QP. All right. So we can assume that G is in the endomorphisms of F, because we can just multiply the powers of P until this is the case. So there's going to be, so ZP here lives in this endomorphism ring, and it's closed in here. So it suffices to show that G is equal to some integer modulo any power of P. Since then we can just take this converging series, which is going to converge to something in ZP, but it's also going to converge to G, so therefore it's going to compose. So therefore G isn't going to be in ZP. Okay. So we go by induction. So pi G of pi inverse is equal to G, since G we assume to be in the center. Let me say G is in the center here so that it's a bit clear. So we're assuming G is in the center. So if we conjugate by pi, then we're going to get right back to G. So if we're going to look modulo P, so we're looking at G of T as B0 T plus whatever else, then pi G pi inverse of B0 is equal to B0 to the power of P, which is equal to B0, which says that B0 is an FP in the residue field. So we can feel free to note that B0 is an integer. So G is equivalent to some integer modulo P, and then we can replace and then we can take G minus this integer B0, and we call this G prime, and then we can continue down because now this is divisible by, so then we can take G prime P inverse and continue on by induction. And then eventually we're gonna get some power series in P, which converges to G, and all its coefficients are integers, so G is in ZP. And as a corollary, a maximal subfield of D is totally ramified over QP. To see this, note that we can just take QP, we can join this pi that we had before, and this is going to be a subfield. A maximal subfield of D has dimension, so if we call it L, then this is going to have dimension 1/2, so the square root of dimension of D, just by general theory of central simple algebras. And in order to see that this actually is, we can note that the ramification index of E QP of pi over QP is going to be greater than or equal to n, which is less than or equal to the degree over QP. Why is it greater than or equal to n? Well, because the pi to the n divides p. And since we have that this here is less than or equal to n, we have equalities throughout. So this is totally ramified of degree n. Okay. So now we're going to find out that we're going to have, if we examine everything we've done so far, we have an exact sequence. So we can take the endomorphisms of F and the units in here, which is just equal to the automorphisms of F. We can include this into the total units in our division ring that we had before. And then the co-kernel of this is just going to be Z, just by the valuation. And on the bottom row, we can take our automorphisms of F, P bar, and F. This maps down here, including into the automorphisms of FP bar by our map from before, which gives us our Frobenius down here, as well as acting on, any element of dx, we can multiply by this unit pi to get into end of fx here. Let me use a pointer. Any element here, we can multiply by the power of pi to get in here. So pi is going to act as an automorphism here of f. And once we get it into some, of fp bar, because pi is acting as Frobenius. So once we get it down into something which is in here, it then acts as an automorphism on f, keeping this field fixed. So we can write it as a product of powers of pi, which is going to include into this factor, and automorphism of f, which is going to include over here. And then we map this into z hat, our total Galois group of fp bar over fp, and this is going to include here. So this becomes, let me call this T and L. T becomes an iso after profinite completion. So L becomes an iso after the same. And we find that we have this dx sitting inside of out fp bar comma f, which gives us some way to look at explicit elements in terms of something simple like this division algebra here. All right. So we have at the end that the formal group law F that we have been studying this has a canonical form over the field fp to the n. So this is going to just be, let's see, sort of by the fact that we had before that the quotient here was fp to the n. So we want to try and figure out what we can do with that. in order to get it down over FP to the n, we have to use descent. So you have to use the fact that you have this, you have these automorphisms of FP bar over F. You can map this out to the Galois group here, as above. In order to get a canonical form over FP to the n, you have to find a splitting of this map over, so not a total splitting, but a splitting over, you multiply out by k z hat here, where k is going to correspond to the fixed field of FP to the n. So this is a subgroup fixing this fixed field. And we want a splitting over this. And in order to do this, we can take any x as an element of D with the nu of x is equal to k. Well, this is for FP of the k. This is just in general. But if we want to take x equals p, then this gives us the canonical splitting here over FP to the n. All right. And in particular, we have a much simpler presentation of our formal group law classifier here. And we can take the spectrum of FP to the n, and we can quotient out by dx over these Fabinii, which we're going to call this group G prime. So that we're going to get an exact sequence G prime over to Z mod NZ to 0 based on the splitting above. So this power of p to the z here is just quotienting out everything which acts trivially down below on this, because p was of degree n, and the nth Frobenius on this is just the identity. So this action factors over this subgroup, and this leads to this exact sequence here. And we say G prime is the Morava stabilizer group. All right, I'm a bit low on time, so I'm going to shift a little bit to Bousfield localizations. We can do this rather quickly, I believe. So the general setup is we're going to start with C, a stable infinity subcategory of spectra closed under colimits. So we also want there to be C0 subset of C, a small generating set, so generating under colimits. So this just says that C is presentable. And in this case, we're going to have, by presentability considerations, the inclusion I from C in the spectra admits a right adjoint. G in spectra down to C. Sometimes we will, I'm going to try and not abuse actually. We'll see if I can go without abusing notation that much. But if we recall this fact from basic one category theory, if C and D are one categories, and we have an adjunction like so, oops. Then the following are equivalent. F is a localization. So this means that D is equal to the universal category inverting everything which becomes everything in C which becomes invertible after applying F. 2, G is fully faithful. And 3, the unit is an equivalence. The same holds infinity categorically, but I just wanted to say that for one categories. All right. So what we note is that this inclusion being fully faithful, because C is a full subcategory, implies that this right adjoint here is a localization. This is by the dual of this result here. So we're going to have spectra sitting here. We're going to have this right adjoint G, and we're going to have this inclusion I. And now, in particular, we actually get another adjoint on this side by what we're going to call these orthogonals to C. And we're going to have this map L here and this inclusion J here. And now in order to define C dual, you can either take a classical way is to take objects which are C local, which means that if Y to X is a map from a so-called C nilpotent object, then it is homotopic to 0. Where C nilpotent means that sorry, should not be saying it this way. I should be saying for every Y and C. Then Y, sorry, then X, then it is homotopic to 0. There's a few other ways you can say this. One other easy way is you can say it's the essential image of a certain map, and the certain map, we can abuse stability to actually get this joint over here. And how do we do this? Well, we take the co-unit of this map here, this junction here, and we're going to have IG of dash. We're going to map by epsilon of dash into the identity. And we're going to take the cofiber of this map. And this is going to what we're going to call JL. So C dual can also be defined as the essential image of this endofunctor. And then we get these two functors for free, which participate in this junction. And one can see that it's a localization by there's certain facts that you can do for L being some idempotent functor. All right. And now Bousfield has some examples where you're going to take some spectrum E. Then you can talk about E nilpotent spectra. Well, even first E acyclic spectra. So this is just the kernel of smash product with E. So these are X such that E, you tensor with X, then you can get 0. And then you can talk about E local spectra as those such that if we have any E acyclic spectrum mapping to it, then this map is 0. And one can sort of participate in the story with what is usually called, so the same fiber sequence that we get here for every element is usually called this in this world. So this is your E localization. This is called the left Bousfield localization. With respect to E. This can be defined as the universal universal E local spectrum with a map from any spectrum X, such that the map is an E equivalence, so it's an equivalence after you smash with E. That actually characterizes it, the fact of being E equivalence to an E local spectrum. All right, and there's some special classes of these that you can look at. So you have, for instance, what happens if you want to try and do this story again and get something over here? Well, the following are equivalent is that this JL preserves colimits. The second is that C, the orthogonal part is closed under colimits. That J has a right adjoint. That if we look back here, G, sorry, we want I to have a the G is going to have a right adjoint as well. So this right adjoint is necessarily going to be fully faithful. And the final one is that G of dash is equal to K tensor with whatever you're looking at for some object K. We can actually prove this very quickly is that, well, one, if and only if two, this follows since if you look at how we defined this, then this is the essential image of JL. So this is closed under colimits if and only if JL preserves colimits, if and only if J preserves colimits, if and only if there's a right adjoint here. If and only if, well, you can use the same sort of trick where you have this right adjoint here. So this is going to determine a another pair of adjunctions down here. And in fact, if you look at these sequences, L here is sort of the quotient by C, I is the kernel of L, J is the kernel of G. So the adjunction down here is going to have to give you a right adjoint to G because this is whatever you get from the same sort of story repeated. So if you look at this part of the story repeated with respect to flipping the story, then G is going, then whatever function you get down here is the left joint has to be the has to have kernel J, and G is going to be universal with that property, so it's going to have to be G. So you're going to get a right adjoint to G, therefore G is going to preserve colimits. And equivalently, if you get a right adjoint to G, then you get the same adjoint above. So if G preserves colimits, so this shows like one if only if two, if only if three, if only if four. And then G preserves colimits if and only if G of X is equal to, well here, right, X is a limit, as a colimit of this copies of the sphere spectrum, which you can do since the sphere spectrum generates spectra under colimits. Nothing requires the sphere spectrum here as long as you're generated under colimits by your unit, then this all holds true. In fact, I think even if you're compactly generated, this holds true. Then what we have here is that G of X is G of this colimit, is the colimit of G of S, is the colimit of K, where we're defining K as G of this G of this sphere spectrum, which is the limit of K tensor S, and then we can just pull the limit into the tensor product. And then this is just K tensor X. And conversely, the tensor product means with colimits, so 5 implies 4. All right. So there's some important examples of when this comes up. For instance, if you take C to be the full subcategory generated under colimits by a set of compact objects, then C is smashing. So we can look at the compact part to find some smashing ideals. These are all tensor ideals since they're generated by the unit. Then your tensor ideal as soon as you're smashing or a thick subcategory of the compact objects. You can ask if all arise this way. It's not true in general. It's not true in general if you look at a general tensor triangulated category. It's an open question for spectra. It's called the telescope conjecture. But if you want an example of where this fails, take K, a local ring, local commutative ring, where m squared is equal to m is your maximal ideal. Then if m is like, if you only have like, if spec K is a point, then you can show that there is actually more ideals in the big category of derived modules versus if you look at dperf. Because dperf of K, the only fixed tensor ideal you can show is just a point, so it's just 0 ideal. But in this big one, you have more. As long as you choose M sufficiently. So if you choose K sufficiently nice, you choose to be some perfectoid field, for instance, then you're going to get more tensor idempotencies, which are going to give you more smashing ideals. Which is this guy here. In fact, this is actually always going to be a tensor idempotent, and tensor idempotents correspond to these smashing ideals. All right, I think I'm done for today because I'm a bit over time.
Thanks a lot. So, are there any questions? Okay, I guess we can wrap it up and stop recording.
I did have a weird question. Did you use the word Frobenian?
Yes.
Oh man, yeah, I was about to
Okay.
say that. That made me crack a bit.
Yeah,
I mean,
I've never heard
it's
that
actually a
before, so
common
that's
use
funny.
word. So I was giving a talk on